ever-expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. A total eclipse. The brilliant sun suddenly obliterated by the black disk of the moon.
You can see this eyeball looking down at you.
Both breathtaking and frightening, eclipses warn us of powerful solar storms that may fulfill an ancient prophecy of chaos on Earth in 2012.
People would freak out. We wouldn't have refrigeration, we wouldn't have lights.
Eclipses of distant stars are now revealing new planets, even other Earths.
Some of them just popped right out at us.
The search covers the entire universe, but it begins here on Earth as the sun hides its face in total eclipse. It's a spectacle in the sky that has enthralled human beings for thousands of years. A total eclipse of the sun. Few people who see one will ever forget it.
Personally witnessing a total solar eclipse in the flesh is an amazing, awe-inspiring, tremendously moving experience. I've never experienced anything quite like it.
Some, like astronomer Glenn Schneider, are part of a subculture of globe-hopping eclipse chasers who will go anywhere, anytime to see an eclipse.
It grips you because the sky has gone dark. Not as dark as midnight, but like a very deep twilight. And you can see this eyeball looking down at you. The black disk where the sun was is the silhouette of the moon. It's an experience that you can't believe it was only a minute or 2 minutes. It seems to have lasted a lifetime, and also just an instant.
This compelling event is a launching pad for cosmic exploration, solving a string of mysteries that have puzzled mankind for ages. What makes the sun disappear without warning? When does it happen? How can we predict it? Can we make it happen ourselves? Once understood, we find that each eclipse reveals something new about the universe. Even now, we're finding our newest eclipses around distant stars, revealing extrasolar planets, some perhaps twins to the Earth, with the potential for life. The story begins with the mystery of our own eclipses. A sun suddenly vanishing in broad daylight. Visible since before recorded history, the ancients regarded eclipses with wonder and fear.
The ancient people didn't understand physically what was going on during a solar eclipse. They would see a progressively bigger bite being taken out of the sun, as though some gods or dragons were eating the sun, mad at those people. So the people would beat pots and pans and yell and scream and sacrifice virgins and all sorts of things to appease the gods and scare the dragons away. And you know what? It worked every time.
Through thousands of years, patiently watching the movements of the sun and moon in the sky, ancient astronomers realized eclipses happen when the moon passed directly in front of the sun. In time, scholars studied the patterns of eclipses, long enough to predict them. The Babylonians discovered what's called the Saros cycle, more than 22 centuries ago.
The Saros cycle is a cycle of eclipses that repeat every 223 months, roughly every 18 years, and they're very similar to one another.
The Greeks were aware of the Babylonian discovery, as we've learned from the remarkable Antikythera mechanism, an ancient device found on a shipwreck under the Mediterranean Sea in 1901.
The Antikythera mechanism was first thought to be some sort of a clock and then some sort of celestial timer. It was a very complex mechanism with many gears and layers and planes.
Archaeologists have been intrigued by the Antikythera mechanism ever since it was found. Decades ago, they understood it was a mechanical computer for calculating movements of the planets, phases of the moon, and other astronomical phenomena. But the latest discovery astounded them. In 2008, using 3D X-rays and CT scans, they found that the Babylonian Saros cycle was built into the device.
In two of the back plates of the mechanism was inscribed a spiral-like figure that had divisions that, when you added them up, corresponded to the months in a Saros cycle. The only reason to have the Saros built into the mechanism was if it was an eclipse predictor as well.
A total eclipse of the sun can be seen somewhere on Earth an average of once every 16 months. Today, predicting them is a very exact science.
The next total solar eclipse to be visible from the United States will be on August 21st, 2017.
But modern astronomers can do much better than supplying the date for an eclipse. An eclipse map shows the exact path along which people can see the 2017 total eclipse. And the timing is down to the second. It will reach totality at 10:17 plus 18 seconds a.m. in Salem, Oregon, at 1:15:55 seconds p.m. in St. Louis, Missouri, and 2:41:55 seconds in Columbia, South Carolina. It will cross the country in 1 hour, 31 minutes, and 1.6 seconds, along a path averaging 66 miles wide. With information so exact, anyone who wants to see it will be able to.
People will have an opportunity to get to the path of totality from all over the United States. It's an opportunity that everybody should really try to take because they're few and far between.
Apart from the spectacular visible picture, the blocked sun also gives viewers the chills, in a literal sense. During a total solar eclipse, the temperature can drop as much as 35 degrees. That, of course, is nothing compared to the temperatures in outer space, where all the action is taking place. How cold can the universe get? That's what Carlo of Boulder, Colorado wanted to ask the universe. So he emailed us. What is the current temperature of the universe? And why is it so cold?
Carlo, that's a really cool question, if you'll pardon my pun. Here near the sun, we feel warm. But in outer space, the temperature of the universe is only 3 degrees above absolute zero. It's really cold. It's that cold because the universe can be thought of as an expanding gas, and it's been expanding and cooling for 14 billion years.
The reason total eclipses are few and far between is the result of a delicate astronomical interplay. It depends on a moon that's an average of about 240,000 miles away and 1/4 the diameter of the Earth.
To demonstrate just how difficult it is to get two objects to align just right to create an eclipse, I'm going to use this ping pong ball representing the Earth and this very small marble representing the moon. This is so small that I have to hold it in tweezers for you to be able to see. Now, the Earth and the moon are located about this far apart in space, and it makes it very difficult for them to align just right with the sun to create an eclipse, as I'm going to demonstrate. It's very difficult to get these to align just right for an eclipse to occur. But once I do, I can see a fuzzy shadow on this ping pong ball that looks very much like the beautiful photographs of solar eclipses from space.
The large fuzzy part of the shadow is called the penumbra. If you're standing in the penumbra during an eclipse, the sun is not completely covered, and you see a partial eclipse. The small, dark central part of the shadow is called the umbra. If you're standing in it, the sun is completely covered, and you see the total eclipse. Because of the moon's motion in its orbit, the umbra moves across the Earth, tracing a clear line called the path of totality, the only place where a true total eclipse is visible.
The width of the umbra is typically under 100 miles. So you really have to position yourself carefully in order to see a totally eclipsed sun. And seeing a 97 or 98% eclipse is nowhere near seeing a 100% eclipsed sun. You've got to be in the path of totality.
There is much more to the eclipse phenomenon than just the sun and the moon. The story reaches across the universe, because eclipses do happen everywhere.
An eclipse occurs whenever one object passes between us and another object, cutting off its light.
Virtually all other planets with moons will also have solar eclipses, whether they occur here in our own solar system or around other stars across the entire expanse of space. But what can this eye candy of the cosmos teach us about the universe? How is it possible that a simple eclipse on the Earth can prove that the bizarre distortions of space and time predicted by Albert Einstein are essentially correct? Our search for total eclipses begins with what we witness from the Earth. In space, satellites use eclipses of our sun to watch for disasters like the fabled solar storms of 2012. But farther out in the cosmos, our explorations reveal that there are eclipses everywhere. Many of them keys to unlocking secrets of the universe. In the solar system, the only planets without eclipses are Mercury and Venus, because they have no moons.
Currently, there's about 170 known moons orbiting planets in our solar system. Now, that number keeps on growing. Saturn and Jupiter each have at least 60 known moons, but as we get better and better data, additional small moons are being found. So I think there are hundreds of moons in the solar system.
In most cases, the moons are too small to block the full disk of the sun. Mars is a good example. Taken from the surface by the Opportunity rover, these NASA photos show the Martian moon Phobos as it moves across the sun. It turns out that the eclipses we see here on Earth are like no others.
In order to get the kind of eclipse that we have here on Earth, where it's a total eclipse, but the moon just fits over the sun so that you can see the corona and how dramatic that is, requires a remarkable alignment of size and distance.
It amounts to a coincidence of cosmic proportions. The sun is about 400 times bigger than the moon. But the sun also happens to be about 400 times farther away from the Earth than the moon. What that means is that both the sun and the moon appear to be almost exactly the same size in the sky. Their sizes in the sky are crucial for eclipses.
Suppose this ball represents the sun and the small red ball represents the moon. To get a total solar eclipse, they have to be perfectly lined up with each other and with the Earth. Now in this case, the moon is too far from the Earth, so it looks too small to fully cover the sun's disk. But as I bring the moon closer to the Earth, the moon looks bigger and bigger. Now eventually, the moon is close enough to the Earth that it perfectly covers the sun's disk. That's a perfect total solar eclipse.
What are the chances that this remarkable alignment would happen on a planet at just the time in its history when an intelligent species has evolved to witness and wonder about the results?
It's interesting to speculate whether any other intelligent beings in our Milky Way galaxy experience such beautiful, perfect, total solar eclipses.
It's really quite possible that we may be the only intelligent species in the entire universe that has this kind of alignment because it is so specific.
And while ancient humans once dreaded solar eclipses for hiding the sun, another kind of eclipse helped to answer what was once a fundamental question. Is the Earth flat or is it round? The puzzle was solved when the Earth and Moon went into a celestial role reversal. The result was a lunar eclipse.
By watching the shadow of the Earth pass across the moon, the ancients were able to actually see that the shadow was curved. Therefore, they were able to infer that since the shadow is curved, the Earth itself must also be spherical.
The curvature is prominent when only part of the Earth's shadow passes across the moon. But when the moon is entirely shadowed by the Earth, the lunar eclipse is total.
A total lunar eclipse occurs when the moon passes within the shadow cast by the Earth. So the moon is completely in the shadow of the Earth. Everyone from the dark side of the Earth can see the totally eclipsed moon. That means a vast population can see a lunar eclipse, whereas only a small number of people can see a total solar eclipse.
Lunar eclipses also helped scientists learn about the scattering of light. In a total lunar eclipse, the moon turns red-orange. It is in the Earth's shadow, but some light from the sun scatters through the atmosphere. The light, passing through a great distance of atmosphere, turns red, just as it does on Earth when the sun is on the horizon. The light travels through its greatest thickness of atmosphere and creates a red sunrise or sunset. In fact, every kind of eclipse has much to teach us about the science of the universe. In the early 20th century, one solar eclipse, witnessed at the White House by President Coolidge, gave us the first confirmation of a prediction made by a young scientist named Albert Einstein.
In 1919, the astronomer Arthur Eddington went to the location of a total solar eclipse to test a prediction of Einstein's general theory of relativity.
In 1915, Einstein published his prediction that gravity causes space to curve, and the light from stars would bend following that curve. So if there were a star close to the sun in the sky, its light would be bent by the sun's gravity. The only way to test Einstein's prediction was during an eclipse, when the sun was darkened and the nearby stars were visible. Eddington knew the accurate position of a star that should have been blocked by the sun. But if the sun's gravity bent the star's light, as Einstein said, it would be seen as if it were in a different position altogether.
Eddington measured that. He saw that, thus confirming for the first time a prediction of Einstein's general theory of relativity.
But the greatest scientific benefit of total solar eclipses is the view they give us of the sun's corona, which is otherwise invisible to us.
Without the occurrence of total solar eclipses, it's really questionable today whether we would actually even know that the sun had a corona, an outer, hot, tenuous atmosphere.
The solar disk is 1,000,000 times brighter than the surrounding corona. And so if you don't block that out, you can't visibly see the corona. For us to be able to observe the corona is important because otherwise we wouldn't know that this layer of the solar atmosphere extends out into space. And in fact, we're embedded here on Earth in the solar atmosphere and the extended solar corona.
For more than 3 centuries after the invention of the telescope, astronomers rushed to far-flung locations all over the world just to spend a few minutes observing, studying, and analyzing the mysterious corona. And it stayed that way until the technological leap that gave mankind the power to make its own eclipses. These artificial eclipses revealed something totally unexpected. Eruptions in space that turned out to be the greatest explosions in the solar system. Eclipses of every kind have proven to be keys to unlocking many of the secrets scattered across the universe. Eclipses reveal planets circling distant stars and solar storms posing dangers to Earth worse than we can imagine. The sun's threats are hidden in the corona, which appears on Earth only during a total eclipse. It happens only once every 16 months on average, at places scattered across the entire globe. Not nearly enough for monitoring such a deadly hazard. Out in space, though, satellites send us up-to-the-minute pictures of the sun. Spectacular space probes show the solar corona in all its glory and never ever have to wait for an eclipse. Their secret is a piece of technology that creates a man-made eclipse.
Let's say I want to look at the sun, which is right next to me here. The sun is really bright and it scatters lots of light in the sky, so much so that I can't see what's around it. But if I use a device like an occluder that an optician might use, I can use it to block the sunlight, kill the glare, and see what's around the sun. I can do the same thing with stars, and a device like that we can put together is called a coronagraph. We use it for studying the sun's corona, and we use it for studying the environments of stars.
Coronagraphs, invented in 1939, were first applied to telescopes on Earth. They work best at the highest altitudes, where scattering of sunlight by the atmosphere is minimized. But coronagraphs do their heaviest lifting in space. 2 of the major missions carrying coronagraphs are the SOHO and Stereo spacecraft. They photograph the corona out to great distances and pick up other phenomena that, without these artificial eclipses, would be totally unseen.
Movies of the sun obtained by satellites are really fascinating to watch because you can see all sorts of changes in the structure of the corona and prominences and flares and things like that. And you can also see what's called sun-grazing comets, comets that come in and nearly hit the sun but go whizzing past. They're too close to the sun to be visible during the nighttime or the daytime, but with the sun's disk blocked out, you can actually see them.
In 1971, a NASA satellite equipped with a coronagraph snapped these shots of something completely unknown. The grainy pictures revealed an explosion in the corona no one had ever seen before.
In 1971, it was discovered with a coronagraph on a satellite that the sun sometimes undergoes what's called coronal mass ejections. Incredibly powerful explosions, like billions of nuclear bombs going off, that eject high-speed charged particles from the sun.
The solar particles speed toward the Earth, where they cause the beautiful auroras, usually seen near the poles. But they can also seriously damage satellites, communications, and power grids. Coronal mass ejections, or CMEs, happen in the corona and are often linked to solar flares, which happen on the sun's surface. These are currently the most powerful explosions known in the solar system, approaching the power of 1 billion hydrogen bombs.
Coronal mass ejections involve so much mass and magnetic energy moving away from the sun. They can be as wide as almost half of the sun, and it's like a large bubble of material and magnetic field moving away from the sun at over 4 million miles an hour.
The amount of solar material ejected is huge. During a CME, mass equivalent to 200,000 World War II battleships is thrown out into space. 220 billion pounds of matter. October 2003. A powerful series of CMEs erupts in the solar corona. One of the most intense in recent memory. It generates auroras seen as far south as Florida. It causes at least one power blackout on Earth and affects more than half of NASA's space missions. The SOHO solar satellite is briefly disabled, but records dramatic pictures of the event.
In the satellite images, you can see the energetic particles hitting the detector, and it looks like there's a bunch of snow. So we can actually see the particles impacting the satellite itself.
But there may be more danger in these solar storms than we suspect. We don't yet know how often the big ones happen. But the latest research tells us the worst-case scenario could smash the Earth with a solar wind whose effects could kill millions. Across the depths of the cosmos, whenever moons or planets cross paths with stars, the result is an often revealing and sometimes awe-inspiring spectacle of an eclipse. Here on Earth, man-made artificial eclipses have uncovered solar storms of incomparable violence. It is critical that we watch for coronal mass ejections, massive solar outbursts discovered using coronagraphs blocking out the disk of the sun. The greatest danger comes when the solar sunspot cycle is at its maximum, roughly every 11 years.
During the maximum of solar activities, there might be 2 or 3 coronal mass ejections per day, whereas during a minimum in the cycle, there might be only 1 per week.
scientists are on the lookout for the next solar maximum, which some believed would come in 2012. That happens to be the year the Mayan calendar comes to an end, which has given rise to widespread speculation about a global disaster in that year. In fact, it's now believed the coming solar maximum will be the weakest since 1928 and won't be reached until after 2012, although precise dating is beyond the realm of today's science.
It is now predicted that the next solar maximum will peak in probably early 2014. Some people predict it will happen before that, but it's a sort of a moving target because we don't fully understand the solar cycle itself.
Scientists have long suspected that a super CME, when it does happen, could be disastrous. The last such event to target the Earth happened in 1859, disrupting telegraph service and creating auroras visible down to the equator. An event like that today would mean power outages on a scale we've never experienced. Much of the U.S. power grid could be down for 3 months and perhaps much longer.
If we lost electricity for 3 months or more, the effects, especially on a country like ours that depends on electricity so much, would be devastating. You can only imagine what it would be like. People would freak out, really. I mean, we wouldn't have refrigeration, we wouldn't have lights.
Without the artificial eclipses in our solar satellites, we would have no idea that such a threat even existed. According to recent estimates, full recovery could take 4 to 10 years. Millions of people could die due to shortages of food, clean water, and pharmaceuticals. Projected damage may be as much as $1 to $2 trillion, comparable to 20 Hurricane Katrinas. A super CME struck the Earth 150 years ago, but scientists disagree on when the next one could come.
The likelihood of that happening in our lifetime is probably not that good, but we just don't know. We don't have enough data.
The most powerful coronal mass ejections that could cause widespread damage over all of Earth probably occur only about once every millennium or so. Nevertheless, having a huge calamity every few thousand years is really a big deal.
Our best protection may be in the artificial eclipses aboard spacecraft monitoring the sun for CMEs. If improved warning systems are put into place, we may have enough time to shut down the electric grid to prevent it from burning out, dodging the deadly bullet otherwise aimed straight for us. A coronal mass ejection may be the most spectacular phenomenon uncovered by eclipse science, but the universe is full of other eclipses, each one teaching us something else about the cosmos. Even a short hop into space, no farther than the moon, turns the tables on us as the Earth becomes the celestial body to eclipse the sun.
Think about how important that Apollo 12 image was, where they turned the camera back towards the Earth and you could see the Earth eclipsing the sun. Those images from Apollo were really epoch-making for humanity. It gave us our first real sense of the Earth as being an object floating in space.
Farther out, the Cassini space probe looks at Saturn, virtually black, surrounded by backlit rings as it blocks out the disk of the sun nearly 1 billion miles away. A very different view of our own moon eclipsing the sun comes from the Stereo B spacecraft. From deep space, the moon appears much smaller, and it crosses the sun's disk in what's called a transit. This kind of eclipse may be pivotal in answering our questions about who else may be out there in the universe.
What makes transits so important is it's one of our ways of actually discovering what are called extrasolar planets, planets orbiting other stars.
The tantalizing possibility is tempered by the daunting problem of actually making it work. Finding a planet transiting in front of its star is like seeing a flea crawling across an auto's headlight. But science is rising to the challenge, and new space telescopes trained on the tiny eclipses that uncover planets around distant stars are about to strike gold. After centuries of wondering, the discovery of another Earth in the depths of space is suddenly within reach. If the search for eclipses starts with the most spectacular examples here on Earth, turning our view out into space reveals other eclipses, not only in the solar system, but far beyond, where they're key to one of astronomy's hottest pursuits, the hunt for extrasolar planets.
A very important kind of eclipse right now is the eclipse that occurs when an extrasolar planet, a planet orbiting another star, passes in front of the parent star. It takes a very sensitive telescope to detect that slight dimming. The most famous telescope project right now is the Kepler Space Telescope that is out there in space looking at over 100,000 sun-like stars and watching over a period of years for the transits of actually Earth-like, Earth-sized planets going in front of those stars.
It'd be great if we could find planets orbiting other stars by simply pointing a telescope up into the sky and taking a picture of one. But that's really tough. One of the reasons that that's really tough is because the stars are about 10 million to 10 billion times brighter than the planets that orbit them. And I can demonstrate that really easily with this searchlight. When I turn it on, you see that I become completely lost in the glare of this light, just as a planet is lost in the glare of the star that it orbits. Kepler's job is to measure the brightnesses of stars, just like we can do with this light meter and our simulated star, the searchlight.
This is how eclipses figure into the mission. The light meter's needle dips when something passes in front of the searchlight, creating an eclipse. Kepler does the same thing, but is so sensitive it can detect a dip of 20 parts per million.
Kepler is capable of detecting an Earth-sized planet around a sun-like star in the habitable zone. So a real Earth-Sun analog, that's what Kepler is capable of doing, and it's the first mission that's capable of doing exactly that.
Kepler is trained on an area of the galaxy containing about 150,000 stars. And it monitors every one of them constantly, measuring each star's brightness every 30 minutes, hoping to detect those minute eclipses caused by planets around some of them. Just a small fraction of them will be in the right position for us to see their planetary transits.
Most of the stars in the sky that have planetary systems don't undergo transits. It's only if we have a lucky chance alignment where the orbital plane of the planet is along our line of sight or contains our line of sight to the Earth that we can actually see when the planet goes in front of the star and dims out some of the star's light.
The very distant combination of light and shadow produces for each transit a telltale light curve showing the dip in brightness as the planet crosses in front of its sun. Kepler produced results after only a few months on the job.
We looked at our very first light curves. We could see transits immediately. I mean, some of them just popped right out at us. The spacecraft was performing flawlessly. The data was beautiful. right out the gate, we were reaching the precision levels very close to what we expected at the beginning.
In January 2010, the Kepler team announced the discovery of the mission's first 5 planets. 4 are gas giants like Jupiter. The 5th the size of Neptune. Kepler saw their transits many times in its first weeks of searching. It means they orbit their stars in a matter of days, eclipsing their stars each time.
These things are closer to their parent star, about 10 times closer to their parent star than Mercury is to our sun. And Mercury's the closest planet to our sun.
But one of Kepler's ultimate goals is to find Earth-like planets around Sun-like stars. And that takes longer, since they will orbit on timescales like our own, once a year.
An Earth-like planet around a Sun-like star is going to produce a dimming of 1 part per 10,000. So it's a very tiny signal. If it's in the habitable zone, that signal, the transit, is going to last 12 hours and would repeat once every year, not once every 3 days. So you have to stare, you have to have stability, you stare for a whole year and you wait for an event that happens and lasts 12 hours and is very, very tiny, 1 part per 10,000.
When Kepler spots the right kind of light curve, large telescopes on the ground follow up. They take additional measurements to be sure the eclipses are caused by planets. It means weeding through a lot of data.
As of June 2010, we had approximately 700 planet candidates.
The confirmation work now being done by ground telescopes is painfully slow and will continue for months and years to come. As the process continues, Kepler's planet list is expected to grow to dozens soon, and later hundreds. Measuring Kepler's success rate is guesswork, but as many as 50% or more of its candidates may turn out to be actual planets. Kepler will search for tiny eclipses for as long as 6 years, accumulating a census of planets in our galaxy more complete than any compiled so far.
Kepler's going to determine if Earth-like planets are common or rare. And the answer either way is going to be very interesting. If it turns out that they're rare, that speaks to how special we are in the galaxy. However, we have reason to believe that they're going to be frequent. I think we're all kind of closet optimists that they're going to be very common, but we don't know. We don't have the answer yet.
In this, the discovery of Earth-like planets around other stars, eclipses will be the tools making it possible. Far removed from the sensory thrill that the chasers seek in witnessing the moon block out our sun, eclipses in deep space may lead us to the ultimate knowledge of our place in the cosmos. By blocking out the light from some of the most luminous objects in creation, it is as if we are screening out the deafening noise and are now hearing only the secret and revealing whispers of the universe.